Okay, so we are live for our review. As I mentioned before, I started posting videos. I wanted to get them all done by now, but clearly that hasn't happened yet. I have the ones for the Lewis structure and the buffers. I'm also going to be making a hybridization one. Where's my list? So after hybridization, we'll go kinetics, and then work on empirical formula with combustion analysis and maybe some gravimetric analysis. It's taking me about an hour, depending on the topic, hour to an hour and a half to create it, which isn't too bad. I should be able, like I said, get one more done tonight and maybe two done tomorrow. We have another Google Hangout tomorrow night. So I'm hoping we'll be productive with that. And then we have, well, the final exam will be Wednesday and Friday, so I'm hoping you guys are prepared for that. But I would be happy to meet. We'll talk about it tomorrow morning. But we have a +1 on Friday then to go over the final exam. So anyhow, I'm hoping some people are going to show up pretty soon because this will be pretty lonesome if I'm doing it by myself. I'm hoping you guys remembered. So I'm looking at the question and answers, and there are no questions posted. And there's no one viewing. So this might not be a good use of time. So maybe I'll talk about something that I think that students have difficulty with that's not already something I'm going to be making a video for. Let me see. Here, I'm going to change views and start writing some of this stuff up. Let's go into that paper. Okay, now I can see some things. You know, I'm having a hard time deciding. How about we go back to I'm sorry. I just did hope there'd be more people watching and talking about it. Let's just talk for a second about electrochem and draw a little bit of pictures and talk about the way that the ions move, because I think that's hard. People don't conceptually think about that very much. So I'm going to make a galvanic cell here. All right. And we're going to connect it with a salt bridge. Let's make the salt bridge green. I don't know why I want to make it green, but I do. Okay. And got a solution in here in each one. All right, and we have some anodes, or not anodes, I should just call them electrodes, because the anode will probably put over here. Oops. It's too bad I'm not an artist, right? And let me pick a good cell, something that's pretty common. I don't have them all totally memorized. Yeah, let's do this. All right, you know what we're gonna do is we're going to do this is going to be copper. So this is copper. And we're going to make, I guess that's gray enough. This is going to be our zinc. And we're connecting them through a voltmeter. Okay. And with salt bridge, it doesn't really matter too much. Let's pick some things that will make it sodium sulfate. Okay, and so you probably wouldn't be able to, I mean, I probably have to give you a chart, but let's just say that on this side, which we've already made it brown, copper 2 plus, oops, no, that's not what I wanted, sorry. I'm going to write these as their reduction. Plus 2 electrons gives us copper sulfate, I mean copper solid. And for this one, the E of the reduction is equal to plus 0.34. That's a positive, okay? And on this side, we have zinc 2 plus 2 electrons gives us zinc solid. And this E of the reduction is equal to negative 0.76. And so looking at that, you can determine which one is actually being reduced and which one should be oxidized. So if you guys remember, whatever is highest on the the reduction potential is the one that is actually being reduced. And in this case, copper is higher with a positive 0.34 and zinc is lower with a negative 0.76. So this is the one that's happening. And if you remember, reduction is happening at the cathode. So I'm going to make, yes. So this is the cathode. Okay, which means on this side, what should be happening is actually zinc, it's a solid, is going to zinc 2 plus 2 electrons, and that's positive 0.76. So if that's happening, zinc solid is becoming zinc 2 plus. That means that off of this is coming out zinc 2 plus. Okay, and on this side, that means that we've got copper. Oh no, it's not copper 2 plus. Oh no, that's right. I'm sorry. Copper 2 plus is going on to there. So it's gaining. This is the cathode. Then this would be the anode. And this is oxidation. And this is reduction. Okay. And okay, so then what's happening inside of here, we'll make this red, is that when the copper 2 plus is going on to, it's going on this electrode, the cathode, that means that Na2 plus is coming out here. It's coming down and coming out. So we're getting Na2 plus. So it's moving this direction. On this side, the cations are building up. And so I'll leave it at SO4 2 minus are coming down this side and coming out the bottom. But you'll notice that I am not drawing the copper, the zinc 2 plus going up this side or copper 2 plus going up that side, because the cations and anions on each side are not going into the salt bridge. The salt bridge is giving off whatever ions are inside of it. And the electrons will make them purple. Electrons going across here. So, and they are going across, because remember, reduction is gain. So our electrons are being added on this side and being removed from the zinc side. So you could say that the anode is losing mass and the cathode is gaining mass. So it's good to know that on the picture what that looks like. And then of course you would know that if you did all these calculations, and we'll make it blue like this, that the E total would be adding these two together. And that's going to be positive 0.34 plus 0.76, because it's you could say the E reduction plus the E of oxidation. And that means it's going to be 1.10 volts. And then from there, you could do calculations involving, identifying delta G. There's lots of different electrochem. We'll just, let's see, you could do, why is it not coming to me at this very moment? You could say that delta G is equal to negative NFE. The N is the number of moles of electrons, which in this case is 2, and the Faraday's constant, which is F. Faraday's constant is 96,485 coulombs per mole of electron. And then you've got the E naught, which is volts. So it ends up being joules, joules volt, or the joules over volts, and they cancel out for E naught. That's where you can get delta G, and then you can plug delta G is equal to negative RT natural log of K. You could solve for K. There's some different things you could do there. Okay, so, and I noticed that Ephraim is on and has some questions, so this is good. So let's answer some of his questions. Let's talk about the first one. The first question Ephraim you have is, can you talk about solving using molar fractions? Let's see. So let's see. Oops. Okay. Sorry, let's see. Okay, so molar fractions. I guess it depends on what you're solving for. It's hard to say just in general. A molar fraction is, so let's see. Sometimes we list them like this. So if you have the molar fraction of some element, oftentimes it's a gas. We say molar fraction of a gas equals the number of moles of your gas over the total number of moles. So, and if you remember about that whole like, oh, I could do it like this actually, that the total number of moles is equal to N1 plus N2 plus N3. And so if you add those all together, you get the N total. And actually, it might be easier if I just did it like this. So N1, the molar fraction of whatever 1 is the N of the total. And you'll notice that it's the same thing, very similar to P total, is equal to P1 plus P2 plus P3. And so, again, the molar fraction or the partial pressure fraction of, it's not coming out very well here, that if you did it like this, pressure of 1 is equal to P1 divided by P total. So you could do it like that. And then you just plug in. I guess I don't really know of an example of what you're talking about. I don't have anything specific to look at. Let's see. Molar fraction. I'm going to try to look up a problem real quick. Sorry, this is taking so long. All right. I guess I'll try this. Let's see. We've got a mixture of 1.10. No, that's not right. I'm already writing it wrong. 1.0 times 10 to the third mole of O2 and 4.5 times 10 to the third mole of helium. And you want to know the mole fraction of the mixture. So the mole fraction of helium would be equal to the 4.5 times 10 to the third moles over the total, which is 1.0 times 10 to the third plus 4.5 times 10 to the third. And then I can put brackets around this down here. 4.5 exponent 3 divided by so for the mole fraction of helium, I get 0.81811, which is 0.82. And then since it's just helium and oxygen, that means you could do the same thing to solve for the mole fraction of oxygen, or you could just subtract it from 1. So 1.00 minus 0.82 equals, for the n of O2 is equal to 0.18. So that's the mole fraction. Actually, what I should have done is, if you guys remember, I forgot to add, I should have done it with the XE. So if we had the X, this is the mole fraction of helium, mole fraction of helium, mole fraction of oxygen, mole fraction of oxygen. So hopefully that answers your question. It's a little bit easier if I had an actual problem to solve it with. But okay, the next one. By the way, you wrote the review was at 11 to 12. That's why not a lot of people are here. Oh, that's unfortunate. I said in class it was going to be 8 o'clock. I wonder why I did that. Hangout review for Sunday tonight. So I wrote that it would be 11 o'clock at night. That would be just straight foolish. I'm not sure where I wrote that. That's unfortunate. On Schoology, all I see is the stuff that I did, but wherever you're seeing it says 11. I don't doubt you. That's a bummer. Okay. Any other questions? Starting to get dried out here. If there's no more questions, I guess I should just work on the video reviews. I'm getting the feeling that maybe that's more productive because the last review was not well attended. I have no idea. On Google+. Okay, great. If there's no other real questions, then I'm going to be done, and I'm going to go ahead and just start working on the review videos. Anything else? Ephraim says, yes, you have more questions. All right. I look forward to getting them. If you could do that quickly. Okay, PES. All right. It would probably be a lot easier if I just showed. I think I have something. Let me see. Oh, I know what I can do. There's a few different images or ways that these can be done. So let me just show you a couple of images and we can go from there. All right. So actually, you know what? I was gonna show you one, but I don't think it's the way that it's gonna be on the test. Let's see if I can get a better picture. Here we go. This will be a good one. All right. All right, so photoelectron spectroscopy, or PES. You can see here, it can be written from like 0 being on the left going to the right, or 0 could be on the right going to the left. You have to really look at your axes to see where it's going from. And whatever the highest or largest amount of energy is the electrons that were the most difficult to remove. It's the most energy. You could talk about it 2 different ways. It's like the energy added to remove the electron, or the amount of energy given, or I'm sorry, yeah, the amount of energy added to remove an electron, or the amount of energy given off. And amount of energy given off when an electron is added. So there's 2 different ways to look at that, but it's usually in megajoules or mega electron volts. And so on the y-axis is the number of electrons. On the x-axis is the amount of energy. So looking at this, it's pretty easy. There's the first line is 1 electron, the second electron is 2 electrons, 3, 4, 5, 6. So if you didn't read any questions below, you could say, okay, the peak that is furthest to the right represents, because that's the highest energy, that's the closest to the nucleus. So that's the 1s. So we've got 1s2 right here. 2 electrons, 1s2. Then we move over to the left, and the next highest is the 2s2. Then 2p6 is that high peak right there. Then 3s2, then 3p1. And so that's how you read those peaks. That'll give you aluminum, as you can see right there. So you would draw that electron configuration. This is just trying to get you to describe where the different peaks are, and identifying the reason, or the rationale, the reason behind this. And then you'd be saying that the amount of energy that is added to remove an electron, right, is more the ionization energy, or electron affinity is when electrons are added, how much energy is given off. And that's that ZF, effective nuclear charge, is the closer it is, the more tightly it's held by the nucleus. As you move further away, you could also talk about shielding, how the 1s or the 2s shields these, and so they're further away, so they're not pulled as tightly by the nucleus. And basically that's about it. That's only maybe a couple questions on the test. Just be aware though that you'd have to identify that and identify what the peaks are, the amount of energy for each one. It's a pretty easy one, actually. You can probably think through it. Okay, a friend's next question. Can you explain what salt bridges do on the molecular level? What kind of elements they prevent from crossing and how? Okay, so let's go back to the drawing that I had done. And it's not about, well, I'll do this. Okay, so I thought I was explaining what salt bridges do on the molecular level. They pass the cations to the side, to the cathode side, because the cathode is losing cathodes. They're losing, not cathodes, they're losing cations because the metal cations are being applied or posted up or added to the cathode. It's gaining mass from all of those copper ions being added on there. And so you're losing the balance of positives and negatives. And so you need to keep that balance in order to, you need to keep that so that you can keep the circuit, keep the electrons flowing. So that's why the cations come onto the side with the cathode, or with where the reduction is happening. The anions go to the other side because as you're adding the cations, as they're coming off of the electrode, off of the anode, you're getting an imbalance there. You're getting a lot more of the positives. And so you're having to add the negatives, the anions, to keep that balance for that charge. And they're not really preventing the elements from crossing. There's just no uptake. There's no reason for there to be an uptake of ions into the salt bridge, because there's a flow out to keep the balance. So that creates a circuit that allows the electrons to pass, or really the current to pass through that. So that's what salt bridges do on the molecular level. I think that explains it. Okay. So your next question is finding the order of a reactions through its half reactions. I have to be completely honest with you. I've not heard of that before. The order of reaction is the kinetics, and half reactions is their redox reactions. And usually you don't find the order of a reaction from its half reactions. Usually you find the order of its reaction through data. It's not like you can look at a reaction itself and determine the order of the reactions. You have to get some data for how a reactant, if you change its concentration, how it affects the rate of the reaction. And so if you're changing the concentration of one thing, usually you have two reactants. And if you keep one of the reactants, well, you have two or more, and you keep one of the reactants concentration consistent, they keep it the same, unchanged, and you change the other one because that's good science, and then what happens to the rate of the reaction? If it doesn't change at all, it's a zero order. If you double the reactant concentration and it doubles the rate of the reaction, then it's a first order. If you double the concentration of the reactant and it quadruples, then it's a second order. So whatever you do to the concentration of the reactant, if it doubles, then whatever you do whatever you do to the reactant concentration, if it's the same effect on the rate, then it's first order. If whatever you do and you square it, so if you triple it, you quadruple it, and then you square that and you have that effect on the rate, then it's a second order reaction. So hopefully that makes sense on the order of the reactions, or at least because I'm not sure about the half reaction stuff. Okay, so you have another question with mechanisms. Okay, let's see if I can figure this out. All right, so it looks like you've written NO2 plus F2 goes to NO2 plus F, and that's the fast step. And then you've written F plus NO2 yields NO2F, and this is the slow step. Okay. Well, you can get the rate law comes from the slow step. And so that's usually the rate is equal to K times the concentration of F times the concentration of NO2. And K, if you remember, it's lowercase k. It's a reaction rate constant. And so that's the same for the reaction at that temperature, for any reaction at that temperature for what that experiment. And in this situation, I gotta say, I'm not really sure. You've got a fast step going here, so whatever you have is producing here. Gosh, I don't know. I don't know. I haven't seen this one before. I got to be honest with you. If you're trying to determine the, let me think about this for a second. Let me still search. I'm assuming that's what you're asking. Oh, these aren't balanced. They should have. I'm assuming this one is 2F. Wow. Okay. I think I may have found what you are talking about. You had NO2 plus F2 yields NO2. Okay, wait. I'm not entirely familiar with what you've written here, but I think I found something that may be similar to it. Let me erase this and start over. I don't know if this is the same thing, but I found something similar. So you have a 2 NO2 plus F2 yields, and this one had a, or actually I don't think it was a 2. Just NO2 F, F2, NO2 F, plus F, and then an NO2 plus F yields NO2F, I guess. And these F's kind of cancel out if you're looking at it first step, second step. So really it comes out to 2NO2 plus F2 yields 2NO2F. So the rate law is equal to rate, or actually not equal to, just write down below. Rate is equal to K, oops. Messed it up there, sorry. NO2 squared, because there's a 2 in front of it, F. And so the overall order, I think I see your next question. Overall order is equal to 3 because there's a 2 here and there's a 1 here, basically. I don't know if that was it or not, but that's what I came up with. Hopefully that was the question you had. All right, Efrain, did you have another question? Oh, good. I'm glad it was the same question. Works out well. Anything else? Well, Efrain, I appreciate that you were asking questions. That makes it hopefully worth your time. I'm sorry we didn't get to more things. I'd hope we had more people, and I apologize if it was. Oh, what is an asymmetrical structure in molecules? Okay. So I didn't think you guys had to do this, so I don't know where that question came from. I don't think you have to do this anymore on the AP exam. They talk about the chirality of molecules. Asymmetrical. So you're basically looking at molecules that if you had there's different ways you can do this, but there's a molecule like right here. So we've got this molecule right here. If it's the same molecule, you'd have the same thing. Or if it has chirality, meaning it has a mirror image, so that's a chiral. It's a chiral carbon because they are left and right images of each other. If it's asymmetrical, you oftentimes get this around like a double bond. And if I actually had you make molecules with this, I'm assuming this is what it's referring to, that it might be something like, if it's an Well, and actually this might not be it now that I think about it. So this has nothing in common. Or they could be referring to, if it's an asymmetrical molecule, they could be saying, okay, listen, we have right, if we have this tetrahedral for hydrocarbon, that's symmetrical. Okay. An asymmetrical molecule might be right. This is asymmetrical because you can't draw a line through this and make it symmetrical on one side or the other. This chlorine and bromine totally throws it off. And you can't cut through. Let's just do this. You can cut through here and it's symmetrical. You can cut through there, it's symmetrical. Through there, it's symmetrical. Here, if you cut through here, there's no symmetry. The chlorine, it's not. Okay, even if you cut through here, then you've got the bromine and the hydrogen they're off. So that's where the asymmetric or asymmetry, we'll say. That could be another way. That's not necessarily referring to the chirality of the carbons, but okay. And so, thanks for answering all my questions. They came from Princeton Review. You know what? Please bring that book to class. I want to take a look at that and see. It helps if it's in context of the question. Sometimes the question is a student question is vague coming out because they're not sure of what specifically they should be asking about. So if I take a look at it, I might be able to help you a bit more. Okay, well, this is good. Then I will, I'll see you guys tomorrow morning and ask me questions. Maybe we could form a little bit better idea of what we want to do at the next Google Hangout, or, well, you guys let me know what you want to do. All right. Thanks, Ephraim. Have a good night. See you tomorrow morning. Bye.